Let's start with the starting point of the calculation. The principal difference lies in its approach, so the principal difference between differential and integral calculus is that the differential calculus is used in the study of rates of change of quantities. Integral calculus focuses on the accumulation of these quantities. Part 1. The first fundamental theorem of the calculus states that we can construct an antiderivative of any continuous function by integration. Part 2. The second fundamental theorem of calculus allows us to calculate the indefinite integral while evaluating the antiderivative at the limits of the integral and subtracting the results.
The reason why integral calculus is closely related to the area under the curve is because an integral represents the sum of an infinite number of infinitesimally small rectangles. By stacking them from point A to point B, we approximate the total area with great precision.
Now I'm going to talk about the definite integral. The definite integral is a fundamental concept in calculus that calculates the sigma area between the graph of a function f of x and the x-axis over a specific interval that could be a or b. Represented by the notation, the integral of f of x from a to b is formally calculated as the limit of a Riemann sum as the number of approximation of rectangles tends to the infinity, and its result can be positive if the area above the x-axis dominates, negative if the area below dominates, or zero if the positive and the negative areas cancel each other out within that interval.
Now that the theory is clear, let's look at the 4 practical steps for solving any defined integral, coarsely of the fundamental theorem of calculus that we just saw. The first step is to determine the antiderivative of the function fx, denoted as fx. This process refers the differentiation establishing the primate function without the need to include the integration constant, since this will be cancelled in the final stage. The second step is to evaluate the integration limits. To do this, the first substitute b for x to obtain fb, and then evaluate the limits, starting with the upper limit and ending with the lower limit. Finally, in the third step, the principle of subtraction established by the theorem is applied. This is done by subtracting the value obtained at the lower limit, fa, from the value obtained at the upper limit, fb. The result of this operation, fb minus fa, is the signet net area of the function in the specific interval. If we have the function fx equal to x plus 3, the graph of this function is a straight line, and if we want to calculate for the area in the interval 1, 4, for example, we will look at the x-axis and locate the x-coordinate equal to 1, which is around here and the 4, and at those coordinates we will draw segment towards where the graph is located, and then we will look at the area that is formed, which in this case is the area here. It is actually called a trapezoid. We will also calculate the area in other ways, but let's see how to calculate it with an integral to calculate the area. This is show. So What we will do is integrate from 1 to 4, which is an integration interval, the function fx, which was 2x plus 3, where we respect to x obviously, and then we do the integral here.
The integral of 2x is x squared and the integral of 3 is 3x. And then we have to evaluate the limits of integration, which go from 1 to 4. 4 for the upper limit and 1 for the lower limit. We always substitute the upper limit first in each x, leaving us with 4. So square plus 3 times 4, and then we subtract the substitution in the lower limit, which is 1. So we are left with 1 squared plus 3 times 1, and here we have to do the operations. 4 squared is 16, plus 3 times 4 is 12. 16 plus 12 give us 28. And here 3 times 1 is 3, plus 1 give us 4, and 28 minus 4 give us 24. This is the area of this figure. So we still have to calculate the area on the graph for this function. But as I mentioned it, the figure is an elementary figure. One of the figures that you learn how to calculate the area in elementary school. It is a right angle trapezoid, and we can also calculate its area as the sum of the bases. The larger base plus the smaller base divided by 2 times the height. There is a formula for the area of the trapezoid. In this case, the larger base is here, the smaller base is here, and the height is here. And we simplify to calculate the measurements. In the case of the larger base, goes from 0 to 11, so it measures 11. The smaller base goes from 0 to 5, so it measures 5. And the height, which will be this one here, goes from 1 to 44 minus 1, which gives us 3. So the area can also be calculated as the 11 multiplied by 5, which are the bases divided by 2 uh, multiplied by 8, which is 3. 11 plus 5 is 16, divided by 2 give us 8, multiplied by 3 give us 24, and we see that we get the same result. Sometimes it is convenient to take into account that the fact that a definite integral is an area, because that took several more steps than doing it directly with a formula. That happens in very few cases, only in elementary figures. But for example, there are integrals such as the square roots and square minus x squared, which represents the area under a semicircle. So there are times when it is better to visualize the integral as an area than try to solve it with a definite integral, because then we will have to do a trigonometric substitution and a lot of other steps. So let's not lose sight of the fact that definite integrals, at least in one variable, represent areas.